Hello my friends and welcome to this 10th video of the series Consciousness as a Modular Phenomenon. In this video we are going to progress in the description of the space X, the larger space of our diagram for describing the formation of conscious experiences as a space of partitions. We are going to talk already about a concrete case of partitions, not about a general topological diagram of this projection between the space X and the space Y. Now, let's start giving a general, let's say, idea of these partitions. Each one of the points in the fiber that we are projecting to the base space where the conscious experience that we experience every day arises, each one of those points we can consider that they are partitions. In the case that we are discussing, they are partitions of a certain object that I am experiencing or even about my internal state. So in general, what we are doing is partitioning, and the partitioning is going to be done according to different scales, and that's the important point. I mean, each one of those x1, x2, xn points in the fiber that we are projecting, we can say that they are partitions at different scales. The scale is one of the kind of factors that we can consider in this partition, but also, for example, that in a certain partition, let's focus, for example, in the partition of a certain landscape that we are observing. When you focus on the landscape, you can perceive, let's say, focus on one part of the landscape and not so much about other parts of the landscape, and to do a partition on a certain scale, very small or very large scale. And that is the interplay between the focus that you are doing in the partition itself and in the scale that you are doing the partition. So there you have two kind of factors, no? So, but the important thing is the following. Whenever you form a conscious experience, focusing, for example, in this visual experience of looking to a landscape, whenever you do that, in every moment that you have a conscious experience, that when you do this projection in the base space, in every moment you don't perceive all the possible partitions of the system that you could do. You could observe the very microscopic, let's say, scale of the landscape or the very large scale, for example. But usually in each moment you select certain scales that you superpose to form your conscious experience, and certain areas of focus in this landscape that you are observing, for example. So the important thing is when we form a conscious experience through this process of projection, we don't focus on all the possible partitions. We kind of select some of them in each moment, and we are always changing the focus and also the scales at which that we superpose. However, the perception of the object that we have is kind of robust, is kind of smooth, let's say, from one point of time to the next one. So that is also has to be taken into account, because in general, if you take all the possible partitions of a certain system and you superpose all of them without any kind of weight, what you will get in the base space is white noise. I mean, it's not the mandala, let's say, disk that we were always saying, that this is just white noise. And so this is a very important point. For example, in our analogy that we did in quantum mechanics, for example, if you have, for example, the fiber represent an equivalence class of a quantum equivalence class of states. So what you are doing is to form the real state, the quantum state, the revival state, like we were saying before. What you do is to assign a certain weight to all these base of states that you have in the fiber, a certain weight to all of them. For example, in one moment, one can be the highest weight, like you do in quantum mechanics. So you have a coefficient in the wave function for each one of the base states, and then you get the summation state, summing all those states weighted by those coefficients. So that represent the probabilities according to the Born rule. So the same thing is what we are doing when we form our conscious experience through partitions. You assign a kind of weight to all those partitions in each moment with different focuses, for example, in the landscape, and with different scales. And so, very important, each one of those points, x1, x2 in the fiber, can be representing different kind of focus in the partition that you are doing, and also different scales. That's very important, because then we put a more concrete, let's say, language on how to talk about those partitions in this space X. Now we are talking about partitions concretely, about properties of those partitions, not about a general set, like it can be an abstract space X. Now it's a space of partitions. Now, the very important thing is the following. You remember that we say in the last video that there is a symmetry in the space X. In the space Y, in reality, there is a symmetry, because if you change, for example, you change the order of the points x1, x2, according to the links, for example, with arcs. Remember that the arcs is what defines the fundamental group in both spaces, the space X and the space Y. And our definition is that both spaces, I mean the projection through the fiber, has to respect the fundamental group between both. So the loops, let's say, have to be kind of conserved. Loops, remember, in the fiber there are arcs connecting the points x1, x2, xn, and they project to loops passing through one point in the Y space. So very important. Remember that there is a symmetry in this fundamental group. Is that I can exchange the arcs between the several x1, x2, xn, and the loops in the base space, they stay the same. They don't change. The projection stays the same. So this symmetry is a symmetry in the Y space, but I mean, it's a symmetry in the fiber, but you can say that in the projection it is kind of broken, because you lose this symmetry. I mean, in reality, it's a symmetry of the X space. You can change this thing and not changing the fundamental group, but in the base space, it's kind of broken. This symmetry is broken. You can imagine also that what you are doing in this projection, this map pi, remember that the space X is in general a space in general more complex, or more, let's say, with a higher dimensionality than this space Y where we are projecting. So you can imagine that the space X is a kind of higher dimensional space than the space Y, because in general what we are doing is projecting equivalence classes. So in general you are losing dimensionality in this kind of mappings. So the more interesting thing is that you can imagine that what you are doing when you are projecting is a kind of dimensional reduction. So you project a space that has a higher dimensionality into a space that has less dimensions. Usually when you say dimensional reduction, what you are talking, if you do it in a smooth process, that we are doing here, because we are talking about Riemann surfaces in the space Y. If you do it with a smooth transformation, usually what you are saying is that you are kind of talking about a fractal, let's say, transformation, a dimensional reduction, for example. Exactly. Usually, if you want to describe the full process, it should be, you are talking about a kind of fractal reduction, something that is passing from a higher dimensionality to a smaller dimensionality. Usually when you have to do that in a smooth process, you have to always introduce kind of a fractalization in the, let's say, the boundary of this mapping. It should be kind of fractal, because dimensional reduction requires this kind of geometric transformation from higher dimensional to smaller dimensions. So this is more or less the path that we are going to follow. If you consider that you are doing a kind of reduction of dimensionality in this mapping, then you have a property in fractals. You have a property that is called autosimilarity. Autosimilarity, that means that the fractal look at a very small scale is similar in form, but not with the same number of degrees of freedom or elements than in a larger scale. So they look, if you look at this fractal in a large scale or on a small scale, they look dissimilar. That's why they call this property self-similarity. So if you, for example, choose several states, and for example, in the evolution, you require that the evolution in the Y plane, it should be kind of smooth, or smooth and robust. And we said in the previous video that this property of that the states that contribute to form the summation in the Y space are not all the possible partitions. Remember that there was a subset of these partitions that were in a kind of p-adic metric relationship between each other. I mean, they were a kind of between each other. These loops in the X space, the length of these loops, for example, can be let's call it L, a kind of L value, but it has to be more or less the same for all of these loops, for example. And remember that we said that the path of the conscious experience is given by this bundle of geodesics in the mandala. Remember that we say that. And that the p-adic metric, this induced metric in the mandala space, it has to be, I mean, the length of each one of those geodesics has to be more or less the same, L. Let's call it L. And this is very interesting if you take into account this fractality, this autosimilarity of the states that we are summing up. I mean, that we choose for the summation. Because if you have autosimilarity or self-similarity, when you do a change in scale, in reality, you are just adding elements. If you consider, for example, path, these arcs, from the length of these arcs, if you are kind of adding in a partition of a landscape, imagine, if you are just changing the scale, the only thing that you are adding is adding elements of the same kind, but at a smaller scale. So, for example, you can imagine, for example, you are pixeling the landscape at a different scale. So you are kind of reducing the number of pixels by a fixed amount for all the landscape. And this is, I mean, the reduction of this kind of fixed reduction in the number of elements is p-adic. The length, let's say, of those elements is the same, even when you are reducing the size of the pixels, for example, in one partition in a landscape. When you are reducing it by the same amount in a kind of square, imagine you are partitioning a two-dimensional landscape. If you do the reduction in a self-similar way, using pixels of square pixels in 2 dimensions, the only thing that you did is just partitioning the scene in a more fine-grained way. But from the point of view of the p-adic metric that is induced in this partition, let's say, both partitions, both pixelations, let's say, of this landscape, they are of the same length, of same weight. Why? Because the self-similarity in the fractal partition makes that the number of elements that appears when you do this partition, this pixelization of this landscape, is in a certain relation, is kind of phase lock. Exactly, it's always phase lock. And the same thing happens with our partitions, with the conscious partitions, the ones that we are for forming this our perception of this landscape. So this is just to give you an idea that if you think, for example, that this reduction is a dimensional reduction from a higher space, for example, higher dimensional space to a lower dimensional space, then you have a kind of fractal transformation there. The fractal transformations introduce the idea of autosimilarity, and this is very let's say, suitable for our idea of dealing with partitions, because partitions will always behave in this kind of fractal way, in this fractal reduction way. If you think, like we say, that we are not going to choose all the partitions, we are going to choose some partitions that behave, that reduce kind of in this self-similar way. Because we could, for example, partition the landscape in ways that are not self-similar. For example, we can choose, I don't know, some forms that cannot be self-similar. But you can choose, for example, in a two-dimensional space, you can always partition in squares. And if you partition in squares, it will be always self-similar. Now, imagine that you are doing this partition, but in a general landscape that is not, let's say, just a square, it's not a rectangle, it just has a lot of forms, a lot of areas of focus, for example, a lot of detail, large scale detail and small scale detail. Imagine that you are doing partition is that. So what you do is to choose areas of focus and certain scales where you are going to do partitions, and then you kind of project all this tower of partitions that are at a certain length, p-adic length of each other. So this idea of the self-similarity as the analog of a metric also for our partitions is something that we were looking for. Remember in the last video we were saying what can be, for example, the idea of a length, for example, in our p-adic length in our partitions, let's say. So a good way of defining this length is this idea of self-similarity. If you have a tower of partitions that is self-similar, and this is a subset that we want to look for, we don't take all the possible partitions, we choose only a subset of self-similar partitions, for example. No? And not all of them, because you could take, for example, all the partitions that are self-similar and sum them up, and you will get also, it's not what we are doing when we are being conscious of this landscape. We are choosing certain partitions. So the important thing is that this symmetry that we have in the fiber, that we can exchange this x1, xn, it has to be broken to be able to form a robust conscious experience. And how we are going to break this symmetry, and this is we start to speak about the idea of symmetry breaking, and it's an idea very important in physics because symmetry breaking is at the heart of, for example, of field theory, of most of the standard model, for example. All this idea of symmetry breaking is there. We are going to make use of that also in our theory, in a way that is that allows us to introduce an idea that you will see in a moment. Why do we need this symmetry breaking? We already said we have to break the symmetry in the X space to be able to form a smooth evolution in the Y space. And so symmetry breaking. And remember one thing more. What we say. Remember that we say that in the phase, we will do the idea of symmetry breaking in analogy with quantum mechanics also. Remember that we say that the phases in the we have a mechanism of phase locking in the fiber. If you consider, for example, those as quantum states, the phases in this fiber that we are projecting, they are phase locked. In general, if you have all possible phases, for example, and you have, if you try to sum up, for example, all the phases, state with different phases, not phase locked, for example, they are going to give you not a revival state, they are going to give you a very disorganized state. So, but when you kind of select certain weights in these phases and you choose states that are phase locked with certain weights, you get the revival state. So you have to break the symmetry of those states that are equivalent in principle by assigning certain weights. And in quantum mechanics, one way of breaking the phase symmetry, for example, you have states that are equivalent from the phase point of view that only differ by a certain phase, and they are completely equivalent. If you want to break this kind of symmetry, one way of doing it is using the Aharonov-Bohm method. In quantum mechanics, you have the famous Aharonov-Bohm experiment where you have to detect the phase of two equivalent states that are, differing only by phase. And you can do that, for example, adding a magnetic field. If you add a magnetic field, you can, in principle, detect the difference in phases in states that are different only in phases, but they are equivalent from any other point of view. So the same thing, we are going to do that. And here, you will say, I mean, what kind of field we can add here. So you will see what is the analogy that we want to get to. So we need to break this symmetry, and we are going to do it using a certain field theoretic mechanism similar to the Aharonov-Bohm mechanism. In general, remember that the famous experiment of Aharonov-Bohm is you have two states that are equivalent and you want to detect it. You put a magnetic field, and then the way, suppose you have two particles, one going in passing in this direction and the other passing in the other direction of the magnetic field. You can detect the difference in phase in the putting a magnetic field between these two particles. For example, if they are photons, for example, you can detect the phase of the different polarization of these photons. So what we are going to do is to introduce a similar idea here, and it's the following. We are going to make a kind of we are going to make a representation of these partitions x1, x2, xn in the x space. We say that they are partitions, so there is a very natural way of representing partitions in mathematics, partitions of any kind, especially, for example, partitions of natural numbers. So when you do the famous partition formula and you want to represent it graphically, you can use the so-called Young diagrams. They represent the partitions of, for example, I will here put an example of P4, for example, P of 4, the partition function, counting the number of way of partitioning a number, for example. P of 4 is equal to 5. You have 5 ways of partitioning the number 4, and you can represent that in Young diagrams. I will put here in a graphic this partition of using Young diagrams. And in general, Young diagrams, when they are when you are, for example, partitioned in two dimensions, you see you can describe the Young diagrams in the border of you can, for example, draw here a kind of vertical axis, horizontal axis, and you can distribute the blocks of the Young diagrams in those axes. I mean, in this boundary of this axis. I mean, you can do the partitions of that. Now, a very interesting thing is that, I mean, the idea is the following. To each one of those partitions, of our conscious partitions, we also assign Young diagrams representing them, because Young diagrams are isomorphic to the partitions of number. And in general, like I told you, I mean, in general, when you are partitioning a set, you can always find a kind of Young diagram representation isomorphic to the partitions themselves. So even if you are, for example, partitioning a landscape, you can kind of associate a kind of graphical representation in form of a Young diagram to that partition. Being that, for example, that you are partitioning in pixels, for example, if it's a two-dimensional landscape, or you are partitioning in some other way, if it's a different space with a different dimensionality. And the most interesting thing is the following. You can, for example, partition you can do this partition of 4 elements, for example, like I say here, without any, in a Young diagram that has so-called no direction. That means that there is no, the Young diagram has no meaning at all. You don't kind of give a kind of preferred direction in the diagram itself. In general, what you do is you put the Young diagram not as a vertical axis in a horizontal axis like here, but you put it kind of as a V diagram. And then you fill the blocks of the Young diagram there. If you don't put any kind of magnetization or field charge in this diagram, then the diagram simply falls in the boundaries of the axis, and eventually some blocks in the middle. However, if you say, for example, that you are going to take a kind of directed Young diagram, which is saying, for example, I draw this Young diagram, but I say that I am in a, for example, gravitational field. So this diagram, the blocks in this Young diagram, they represent kind of mass, and they are going to fall down if I put them in an unstable configuration. And this allows you to draw Young diagrams that are kind of directed or magnetized, you can say. I will give an example here where you can get, for example, the directed Young diagrams compared to the undirected Young diagrams. They are called directed because they have a kind of magnetization or gravitational meaning in the sense that the unstable configurations of those Young diagram blocks, they are kind of eliminated. They say, for example, an unstable configuration, I don't consider it as valid as partition. And you will see, for example, that the directed diagrams of the P4, the partition of the number 4, for example, it gives also 5, but there are some diagrams that appear that are not completely in the boundary that which these two axes that we selected before. So imagine now that you increase the number. You say, for example, P of 100, for example, this is an enormous number, a big high number, no? And you try to do the directed number, the directed Young diagram representation. So what you are going to get is a lot of partitions, and many of them are falling over these two axes, this V axis that we selected, but some of them are going to be stable configurations of these Young diagram blocks, let's say, that fall inside this two-dimensional V that we have there. And the interesting thing is the following. As you increase the number, you are going to get more and more stable configurations of these directed Young diagrams that has a kind of that feel inside this V a kind of parabolic form. You see it more or less in this graphic that we have here. You will see more or less that you are going to get more and more stable configurations that feel kind of a parabolic form or circular form inside this two-dimensional V directed diagram. Now, you saw that the fact that we broke the symmetry from the undirected to the directed by adding a kind of field there, can be a gravitational field, or can say that you magnetize kind of this Young diagram, this undirected Young diagram. This fact introduced that the stable configurations, they are going to kind of sum up when you do the summation of some of those Yann diagrams. And now we are summing Yann diagrams, not the partitions themselves, but the Yann diagrams that are isomorphic to the partitions. If you start superposing the Yann diagrams that are directed, what you are going to see is that what you are going to see is that this kind of parabolic boundary or kind of circular boundary that you see forming there in those stables, it gets very visible, if you assign a kind of weight and you kind of superpose in 2 dimensions many of those directed Yann diagrams, what you are going to see is that appears kind of boundary there, kind of parabolic boundary or circular boundary, superposed to a lot of noise, of course, of less important or less weighted, let's say, partitions. But what you're going to see is it appears a concrete line. So the appearance of this boundary in this directed 2-dimensional Yann diagram, or the superposition, is directly connected to the magnetization, to the directionality of the Yann diagram. That means that what you did is to break the symmetry, adding this magnetization, this direction in the Yann diagram from the undirected case. What you did is to break a symmetry. You break the symmetry exactly in the same way that you did it in the Aharonov bomb experiment, adding a magnetic field. In this case, what you see is that the appearance of this boundary is directly related to this symmetry breaking. Now, let's go further. Our partitions in general, they don't have to be represented in general with a very simple diagram, because our degrees of freedoms are manifold. I mean, we perceive this landscape, yes, but we also perceive, for example, sound in this landscape. We also smell things. We also have an internal state. We see many depths in the field, for example, of this landscape. So the number of dimensions that we are superposing, I mean, in the number of variables that we are taking into consideration for forming our conscious experience is enormous. It's not simply a pixelization of a landscape. It's much more that we are doing. So in general, what we are going to need is to have Yann diagrams that will be isomorphic to our partitions, to these points x1, x2, xn, will be higher dimensional Yann diagrams. You have in mathematics higher dimensional Yann diagrams that is isomorphic to partitions of very complex partitions. For example, you can represent them through higher dimensional Yann diagrams. And I will put some pictures here to show you how they look like, and you will recognize something very interesting. When you do directed Yann, I mean, if you don't break the symmetry, if you consider undirected higher dimensional Yann diagrams, when you sum up them, you get kind of white noise. You don't get any kind of structure. But if you use directed higher dimensional Yann diagrams, you will get more or less the same situation that we saw before with the 2-dimensional ones. You are going to get a kind of boundary generated. Let's say that you project these higher dimensional directed Yann diagrams. You project them, you reduce the dimensionality to 2 dimensions just for visualization. What you get. And you will see that what you get This graphic that I'm going to show you here is what you get from the superposition of a high number of directed higher dimensional Young diagrams when you project them into dimension. And you will see what is this that we have here. Is a mandala space. Exactly. You have a very clear appearance of a boundary, very similar to the mandala space. You have external, let's say, part of the partitions that are glued, let's say, to the two-dimensional box, to the external part of the partition of the of this box two-dimensional, but in the middle you get a very complex pattern, very similar to the mandala space that we have, and a boundary that appears not magically, it appears in the same way that appears this two-dimensional case. What you see, this parabola or this circle appearing there, in the same way appears naturally this kind of circular boundary here. And my proposal is the following. This is the way that a mandala space appears when we use partitions. And this is the way that this boundary appears naturally in the summation process of our partitions. And so this is a concrete realization of the idea of the mandala space for the concrete case of partitions. What I say is that in reality, the Young diagrams, the higher dimension Young diagrams, the summation and directed ones, I mean, when the symmetry, when we break symmetry, through the addition of something that we can call a field, but we are going to have to define what is this field, this symmetry group, this symmetry breaking mechanism. We have to define it, but let's say the idea is the following, that in our case, in the case of the partitions, we have a very natural way of generating the mandala space itself through the summation of this set of higher dimensional Young diagram, directed Young diagrams. And if you do it with undirected ones, you are not going to get more than white noise. But if you break the symmetry, and if you do it with directed higher dimensional, you get, and it's unavoidable, you get this kind of space as in the summation, if you project it in 2 dimensions, no, for example. And then this is a concrete realization of the mandala space for partitions. This is a very important step in our theory, because it demonstrates that there is a mechanism to do all what we have been discussing up to now about mandalas when you talk about partitions, when your fiber represents partitions. So this is a kind of very elegant way of doing, and also a concrete mechanism to generate all this mandala space with a concrete realization. We are going to represent each one of those points x1, x2, xn with higher dimensional directed Young diagrams, which are discrete isomorphic to partitions. So we are going to leave here this video because it's a lot of material, but I hope you see that we have finally, let's say, given some flesh to the idea, to this idea of how to generate this mathematical structure when we talk about partitions. And the fact that we are talking about partitions, it allow us to get all this isomorphic representation in higher dimensional Young diagrams, and the projection in 2 dimensions of that is unavoidable a mandala space. And this is a very, super non-trivial, let's say, consequence of the fact that we are talking about consciousness on the language of partitions. We have now a basis to, let's say, to explore what is the mandala space, knowing what is the mechanism of formation of those mandala spaces in the case of partitions. So let's leave here this video because it's part of the heart of the theory, a kind of motivation why all this makes sense when we talk about partitions. So see you in the next video. Thank you.